So when the nucleophile attacks in an SN2, it is always from the opposite side, and therefore we say that there is inversion of configuration. In SN2, there is 100% inversion of configuration because of backside attack of the nucleophile. It is observed that generally primary and secondary substrate take part in SN2 reaction, whereas tertiary substrate do not generally undergo SN2 reaction. Why? So if you see the structure of this is your primary, this is your primary, this is secondary, and this is tertiary. Tertiary has bulky groups. For example, tertiary butyl group, the smallest group is methyl, and there are 3 methyl groups. So if nucleophile starts attacking from backside, there is steric hindrance, and because of that, backside attack becomes impossible. Therefore, such kind of substrate will never undergo SN2 reaction, rather it will prefer the SN1 type of reaction. So here we have shown that your nucleophile will always approach from the opposite side of the leaving group when it is SN2. So let us check again how exactly this reaction occurs. So if this is your optically active S2 bromobutane, which is optically active, and iodide is coming from the backside of the leaving group. Iodide is a good nucleophile as compared to Br. It is a strong nucleophile as compared to Br. Therefore, it can replace Br. So whenever this reaction takes place now, here Br is replaced by I. So this is an example of SN2 type of reaction. You get only exclusively one product with the inversion of configuration 100%. Now here S2 bromobutane, which is optically active, is converted into optically active R2 bromobutane. So this is your reactant, where you'll find that the orientation of these 3 groups is exactly opposite in the product site, and the configuration is also S is converted into R. We call this as a 100% inversion of configuration. Such kind of reaction is called as stereospecific reaction, where you get only one product, and that is with inversion of configuration. So this inversion of configuration is also called as Walden inversion. It is also known as the flipping of umbrella. If let's say this is your umbrella, then this umbrella is flipped exactly. You will see that if there is a breeze, when there is a rain, you'll find that it gets inverted, and this is how the umbrella look like. Same thing happens. My leaving group and nucleophile, they are opposite side. So methyl group is a primary. This is a primary alkyl halide. They will always undergo SN2 type of reactions. Secondary alkyl halide is a question mark. It depends upon R. What R groups are attached. Sometimes they go via SN1, sometimes they go via SN2, whereas tertiary alkyl halides will always undergo SN1 type of reaction. They will never undergo SN2 type of reaction. So in general, we'll always say that primary alkyl halides undergo SN2 reaction, tertiary alkyl halides undergo SN1 type of reaction, whereas secondary, depending upon its structure and groups attached, sometimes it undergoes via S. Then it depends upon what type of solvent you have used. It also depends upon what nucleophile is there, with what this reaction is going to take place. All that will decide whether this is secondary alkyl halide will undergo SN1 or SN2 type of reaction. So again, here we have shown that your hydroxyl group occupies the position exactly opposite, and you get the inverted product. So this is my umbrella, and this is flipped umbrella, and this is inversion of configuration. So this is how we will always show the example, where we show that SN2 is a stereospecific type of reaction. So some other examples we can see here. S2 bromobutane is converted to R2 bromobutane. Now this is a secondary alkyl halide, where Br is a leaving group and hydroxyl is a nucleophile. First step, that is formation of transition state, is a slow step, and then fastly it undergoes formation of product. Here again we will check that OH and Br are to the opposite side. S is converted into R. This is another example. Cn minus is a nucleophile. And here CBr bond is a polar bond. Br is a leaving group. So whenever they attack, again, this is a secondary alkyl halide. After attack, you'll find that you get a product. S is converted into R and it is an inversion of configuration. Another example, if I take here SCH3 minus is your nucleophile, Br is a leaving group, so SCH3 minus will attack this carbon, Br will go leaving group, SCH3 minus come from opposite side. If Br is at beta position, SCH3 is going to the alpha position, and the configuration again here is converted from S to R. But that doesn't mean that always you will get the opposite configuration. One example we have seen that there is conversion of R into R, but still we will say that there is inversion of configuration because the orientation of groups is totally to the opposite side. If I start with racemic cis, I get the racemic trans because in racemic you'll have R and S both, and both will be converted into their opposite configuration. Here azide, NaN3 is there, N3 minus acts as a nucleophile, replaces Br, and you get the product. Now here you can see a beta, and the incoming nucleophile has gone to alpha position. So all these examples are of your SN2 type of reactions. So what are the different factors now which decide the rate of SN2 type of reaction? So this is your general SN2 reaction. We'll talk about first structure of substrate. In substrate you have two parts. One, what type of substrate, whether it is primary, secondary, tertiary, and what is the nature of leaving group. So R, just now we have discussed that if it is primary, reaction of SN2 will be faster, tertiary, it will be slowest rate. If I take N-butyl, isobutyl, then the secondary butyl and tertiary butyl substrates, you'll find the tertiary butyl never undergo, this is the structure of tertiary butyl, and you know that these three methyl groups will never allow nucleophile to come from the backside. Such kind of substrate will never form a SN2 type of product. Whereas this is primary, so these two will always undergo SN2 type of reaction, whereas this may or may not undergo SN2, but tertiary will always undergo SN1 type of reaction. Then depends upon what is X now. So generally it is found that a good leaving group, a larger size leaving group. So if I take halides, I know that if I go from top to bottom in this group, fluoride is the smallest, fluorine is the smallest, then you have chlorine, then you have bromine, and then iodide. So iodide becomes the best leaving group, and that will show highest rate for SN2 reaction if I compare with fluorides or chlorides. Poor leaving groups, they will not enhance the rate of reaction. The rate of reaction will be slow for SN2. If I take hydroxyl, OR, and NH2, you'll find that these are the poor leaving groups and their rate of reaction will be slower for SN2 type of reaction. Then another factor comes, that is nucleophile. Nucleophile also takes part in rate determining step. So we know that in SN1, nucleophile does not much affect the rate of reaction, but SN2 rate of reaction is affected with the nucleophile. As the concentration of nucleophile increases, the rate of SN2 also increases, and a good nucleophile will always have high rate of reaction. If I take in a period, you take the example of second period elements, carbon, nitrogen, oxygen, and fluorine. They are in the same period. So you'll find that the size of carbon is larger as compared to nitrogen. Nitrogen size is larger than oxygen, and oxygen size is larger than fluorine. So if the size increases, polarizability increases, and they become good nucleophiles. So here CH3 minus, the rate will be higher, whereas F minus, the rate will be very slow. Just as I have seen that in any given group, when I go from top to bottom, the size goes on increasing, and therefore they will have better nucleophilicity if the size is large. You take another example where now oxygen, sulfur, and selenium, they all belong to same group. Oxygen is the smallest, then sulfur, and then selenium. So you'll find that selenium will be a better nucleophile as compared to oxygen containing. Or if I take phosphorus and nitrogen, phosphorus is more polarizable, larger size than nitrogen in its group, and therefore this particular phosphorus nucleophile will have better nucleophilicity as compared to nitrogen compound. So if I take OH minus and H2O, OH minus will be a better nucleophile as compared to water. This is because just now we have discussed that if the concentration of negative charge is higher, then that becomes a good nucleophile. So this is a neutral molecule. This is H2S is also a neutral molecule. And if I compare them with OH minus or SH minus, you'll find that the electron donating capacity of OH minus or SH minus is better as compared to water and H2S, and therefore OH minus or HS minus, SH minus, they're good nucleophiles and they will enhance or they will favor the SN2 type of reaction. Similarly, if I take OH minus and CH3CO minus, you know that CH3CO minus, no doubt, negative charge in both species is on oxygen, but here oxygen is attached to carbonyl. Carbonyl is electron withdrawing. It takes electron from oxygen. The electron density on the oxygen of acetate anion is less as compared to hydroxyl, and therefore hydroxyl will be a better nucleophile as compared to acetate anion. So these are the few examples where you'll find that various products can be obtained. Very important reaction for in organic chemistry, because so many products can be obtained by this SN type of reaction, and these are the examples of SN2 type of reactions you can always go through. So here we finish with the SN2 type of reaction. We have studied about mechanism, stereochemistry, kinetic study, and what are the factors which will affect the rate of SN2 reaction. Based on that, these are the few questions you are supposed to answer and get back. So try to answer this question, and we will discuss about these things in the next lecture. In the next module, that is third module, we'll be talking about what is SNI type of reaction, what is the comparison of SN1 and SN2, how do I decide whether reaction will go